Hello, College Algebra. We are on 9.1 Intro to Probability. This is kind of where we're going to end our school year. So you've done probability before in the past, but these are two methods to find the probability of certain events. So you may or may not have seen these before. So our goal is to find the probability of events using probability tables and tree diagrams. So we are kind of ending and beginning the year. So let's read. After being in my class for almost the entire school year, it would still probably surprise you to find out that I am a level 42 Dungeons & Dragons master. In D&D, there are 4, 6, 8, 10, and 12-sided die. Think of the possibilities, or should I say probabilities. That's right, we're beginning and ending our school year with a probability unit. So we are going to find different methods to help us find probabilities of different events. Okay, let's start with area models of probability. So area models are made to show the probability of different events happening. We have one event, one 6-sided die being rolled, and the area of that square is the probability of that event. So the probability of rolling a 1 on a 6-sided dice is 1/6. The probability of rolling a 5 on a 6-sided dice is also 1/6. So similarly, we have an 8-sided dice where each number has a 1/8 chance of being rolled, and a 10-sided die where each number has a 1/10 probability of being rolled. So we can use these diagrams to answer some questions about probability, find the probability of different events. Let's look at the first question. Find the probability that rolling an even number given that you rolled a 6-sided cube. So let's go to our 6-sided cube and use the diagram to help us. Where are my even numbers? 2, 4, 6. So we're going to add those together. 1/6 plus 1/6 plus 1/6 is 3/6. And one thing to always remember in probabilities, you always simplify your fractions. So that is key. 3/6 is equal to 1/2. So that is the probability of rolling an even number on a 6-sided cube, which that makes sense. Think about it. 6-sided cube, half the numbers are even, half the numbers are odd. So you have a 50% chance of rolling an even number. Let's go to the next question. Find the probability rolling a number greater than 4 given that you rolled a 10-sided cube. So let's go to our 10-sided cube. We want to find the probability of rolling a number greater than 4. So any number, 4 does not count. Any number greater than 4 is going to be in this calculation. How many numbers is that? 1, 2, 3, 4, 5, 6. So 6 out of 10 chances of rolling a number greater than 4, which then simplifies to 3/5. And last but not least, rolling a number 1 or a number greater than or equal to 4 on the 8-sided cube. So again, highlight all your options. We want to find the probability of rolling the number 1 or a number greater than or equal to 4. So that includes all of these numbers. So remember, when the word or comes into play, that means no matter either or means I would win or goes into my probability. So the number that is 1, 2, 3, 4, 5, 6, 6 out of 8 chances of rolling that event, which is 3/4. So use the probability of or the area tables to help you calculate the probabilities of certain events. The notation for probability, so if I say the probability of an event, the probability of rolling an even number. So that's just a way of notating that. P of whatever that event. This little bar here means the probability of event given that another event already happened. So this means given that another event already happened. So that would be like the second one. Okay, moving on. Pretty simple. Let's complicate things more. What if I rolled a 6-sided cube and an 8-sided cube at the same time? So before, we were just rolling one cube for each question. Now we're rolling both of these cubes, and we need to determine different probabilities of different events happening. Okay, so we have, when you're making these area models, you need to put the probability of each event happening for each dice on the outside. Now, what would happen if I asked you to take the area of this square right here? Well, the area, or sorry, not the square, the rectangle. The area of 1/8 times 1/6 would be 1/48. Well, since it's the same for all of those, the area of any one of these squares would be 1/48. And so on. So every single one of these squares is going to have that area of 1/48. So to find the area, you just multiply the row by the column probability. Now, the probabilities might not always be the same throughout, depending on your situation. But in this specific situation, 1/8 times 1/6 is going to be 1/48 each time. Okay, now let's use it to answer some questions. Find the probability of rolling a sum of 9 from the 2 dice. So we need to look at the intersection of the 8-sided dice and the 6-sided dice and which ones would give me the sum of 9 if I rolled the 2 dice. Well, 1 plus 8 equals 9, right? 2 plus 7 equals 9. 3 plus 6 equals 9, so that's this square. 4 plus 5 equals 9. 4 plus 5 again equals 9. 3 plus 6 equals 9. So remember, all of these have that 1/48 chance. So I can use this model to find the squares that fit what the question's asking. Those 1, 2, 3, 4, 5, 6 squares satisfy this event. So I have a 6/48 chance of rolling the 2 dice and their sum being 9, which remember we need to simplify that to 1/8. I have a 1/8 probability of rolling the 2 dice and their sum being 9. Let's look at the next question. Find the probability of rolling a sum of at least 10, given that you rolled a 4 on the 6-sided cube. So we have two things going on here. So we need to kind of find the intersection between these two events. So let's kind of break this down. So I'm going to first highlight, let's do green, the sum of rolling at least 10 on my chart. So at least 10 of a sum. So the first sum of 10 is right here, 6 plus 4. Sum of at least 10. Second one would be 7 plus 4. 8 plus 4. Anything kind of on this side of the diagram. Now, it wants to know, given that I've already rolled a 4 on the 6-sided cube. So we're looking at the 4 row here. So we can kind of ignore this now. So on the 4 column, on the 6-sided cube, and rolling at least a 10 would be the intersection of these two events. So that's 1 over 48 again, 1 over 48, 1 over 48. So we have 3 squares that satisfy the two events. So given that I've already rolled a 4 on the 6-sided cube, find the probability of rolling a sum of at least 10. So that's 3 out of 48, which is equal to 1/16. Alright, next we have find the probability of rolling a sum of 7 or 11. So that means the probability of either one happening. So all of the sums of 7 and 11 work for this question. So let's start with 7. 6 plus 1 equals 7. 2 plus 5 equals 7. 4 plus 3 equals 7. 4 plus 3 again equals 7. 5 plus 2 equals 7. 6 plus 1 equals 7. So that's all of the sums of 7. Remember, these are all 148. Okay, so 1, 2, 3, 4, 5, 6. That's 6 out of 48. Or, so I got to add the next option, the sum of 11. So I'm going to go back and keep highlighting. The sums of 11, we have 8 plus 4. I'm sorry. 7 plus 4. My math is not working. 8 plus 3, 6 plus 5, and 6 plus 5 again. So all of those sum to 11, and that's 4 out of 48. Adding those together, we get 10 out of 48, but when we simplify, we get 5 over 24 for that. And last but not least, we have, to defeat the ogre, you must roll a sum of 2, 5, or 7. What is the probability of beating the ogre? Okay, so we need to take the probability of rolling the sum of 2 plus the probability of rolling a sum of 5 plus the probability of rolling a sum of 7. So let's see. Sum of 2. Let me pick a different color here. Okay, so that's 1 plus 1. Oops. 1 plus 1 is the only sum of 2 that I have. So that's 1 over 48 plus the sum of 5. So 5 is 4 plus 1, 3 plus 2, 3 plus 2 again, 4 plus 1. So we have 1 over 48 plus the sum of 5. There was 4 out of 48. And then for the sum of 7, we have 6 and 1, 5 and 2, 3 and 4, 3 and 4 again. We already kind of did that up there. 1, 2, 3. And we have 6. Over 48. So when you add those together, we have 11 over 48 chances of winning the game and beating the ogre. It's kind of complicated. I know it looks like a lot, but the key is finding the area of each square for your probability and just answering the question at hand by looking at the diagram. So let's look at a couple more scenarios. This concept of area models of probability extends beyond D&D. So they're not as much fun, but still applicable. Let's look at an example. Alright, so here's where we can make this applicable. Zach and Nick, both from the U.S., are shipwrecked on a desert island. Zach has been injured, losing blood rapidly, and Nick is the only person around to give him a transfusion. They made the equipment out of coconuts. Binge watching Gilligan's Island finally paid off for them. For example, in the U.S., 45% of people who have type O blood, 40% of people have type O blood, 40% have type A, 11% have type B, and 4% have type AB. Okay, so we're definitely going to need that information. According to American Red Cross 2004. While there are other ways in which people's blood can differ, this problem will only take into account these 4 blood types. So first it's asking us to make a probability area model representing the blood types for this problem. So we're going to list all the possible blood types that Nick and Zach could have. So it gave us 4 blood types. We're going to make one side Nick and one side Zach. We don't know right now what blood types they have yet, but it said the only options right now are A, B, and O. So Nick or Zach could have A, B, or O. So we're going to list those options out to the side. So they each could have A, B, or O. A, B, or O. Now underneath those or next to it, we're going to list the probability that it said of having each blood type. So it said 45% of people have type O. So we're going to put 0.45 out here. 40% have type A, so that goes here. 11% have type B. And 4% have AB. So remember, it's 0.04. Now, to find the probability of any of these options, we're just going to find the areas. So say I asked you, what's the probability that both Nick and Zach have type A? You would look on the chart and go to A, and their intersection, and their probability would be 0.16, because I took the area. 0.4 times 0.4 is 0.16. So there's a 16% chance that both Zach and Nick have a blood type. So find the areas with your calculator of all of these squares. So 0.4 times 0.11, 0.044, 0.11 times 0.11, 0.0121. So then you kind of fill out the chart of all the areas. And I'm taking this times this to get the area of that for all the squares. So they're not always going to have the same like we saw up here, where they were all 1 over 48. Sometimes your areas will differ. But this is really helpful when you're asked a question, because then all you have to do is go to your chart. So if I were to ask you, once this is filled out, what's the probability that Nick has B and Zach has AB? You would go to the intersection of B and AB right there, and your answer would be 0.004. So these can be very helpful when answering different questions. Okay, so let's read the question that it's asking. What is the probability that Nick and Zach have the same blood type? Now we have to be careful with this question because it didn't give us a specific blood type that it wants. It asked what's the probability they have the same. So what's the probability they both have A? What's the probability they both have B, both have AB, or both have O? So to have the same, that means they both have A, both have B, both have AB, or both have O. Alright, so we're going to take all of those probabilities from our chart and just add them together. So let's look. Both having A would be 0.16, AB, so right there down the middle diagonal is where they would have the same blood type. So both having A is 0.16, both having B 0.0121, AB 0.0016, and both O 0.2025. So if you add those all together, you get 0.3725. So it's about a 37.25% chance they would have the same blood type and they could donate if they were wrecked and needed a transfusion. Okay, so let's read the next question. Type O is considered a universal donor, and it is compatible with other blood types. Scenario 1. What is the probability that Nick can save Zach's life given that Nick has type O blood? So let's think about this. The probability of having the same blood type plus the probability that Nick has type O. Now, we have to here think about an overlap because the probability of having the same blood type, we can look right up here. But we want to add in the probability that Nick has type O, but we'll have that number 0.2025 in there twice. So we need to subtract that out. Okay, so now let's look. What's the probability that they have the same blood? We just found that out right there from the previous problem. 0.3725 plus the probability that Nick has type O minus the overlap that they both have type O. So this is the probability they have the same blood type, probability of any person having type O by themselves, minus the overlap of them both having type O. You get 62%. Okay, let's look at the next one. Scenario 2. Zach has type AB blood, which can only receive transfusions from O or AB. Without knowing Nick's blood type, find the probability that Zach will get a blood transfusion needed to live. Okay, so I'm going to erase to give myself a little more room. Let's think of this scenario. So, we want to find the probability that Nick has AB, given that Zach has AB, plus probability that Nick is O, Nick has O, given that Zach has AB. So there's two options here that can give him the transfusion. If Nick has AB and Zach has AB, they're a match. Or if Nick has O and Zach has AB. Those are our two options that we want to calculate. So if we go to our chart, Nick has A, B, and Zach has O. So if I go here, Nick has A, B, Zach has O was right here. That's 0.0016 plus the other one. Nick has O and Zach has AB. That's right here. 0.018. So you read what it says, go to your chart to find your results. 0.0196. So that is the probability, without knowing Nick's blood type, that Zach will be able to give him the transfusion needed. Okay, let's go to the next one. Rimshot McGee has a 70% free throw average. The opposing team is ahead by 1 point. Rimshot is at the foul line in a 1-on-1 situation with seconds left in the game. A 1-on-1 situation means the player shoots a free throw. If they make the shot, they are allowed to shoot another. If they miss the first shot, they go to the second shot. Each shot is worth 1 point. Set up an area model. Okay, so first we need to set up an area model to kind of go for this situation. So first shot. So the first shot, he can either make it or miss it. There's really only two options. Okay, so he has a 70% chance of making the first shot and a 30% chance of missing because his free throw average is 70%. Now let's come to the second shot. The second shot, he can either, so say he misses the first shot, that's all, then he's done. So if he misses, we kind of just have to leave this blank because after that he's done. But say he makes the first shot, then he gets a second shot. So we're going to come over here for the second shot. We're going to break this into two. For the second shot, he can either make or miss it as well. So his make average is 70% and his miss average is a 30%. Now let's find the areas of these possibilities. So the probability that he makes the first shot, then makes the second shot, is the area of this square. 0.7 times 0.7 is 0.49. The probability that he makes the first shot but misses the second shot is 0.7 times 0.3, is 0.21. And last but not least, probability that he misses the first shot is still just that 0.3 because if you missed, you missed. So if you miss the first shot, you don't get a second. Okay, so now we have a couple options. It said if they miss the first shot, they do not get the second. Each is worth 1 point. So we want to find the probability that they tie the game, win the game, or lose the game. So we're going to kind of make a little chart here to work out our possibilities. So this is the first shot, second shot, the outcome, whether they win, lose, whatever, and the probability. Okay, so the first shot, say he makes it, but the second shot he misses. The outcome would be he ties the game, and the probability we found was 0.21. Okay, so if he makes the first shot, makes the second shot, then they win the game. And that probability we found was 0.49. If he misses the first shot, he doesn't get the second shot, which means they lose the game. That was 0.30. So, to tie the game, the probability is 0.21, to win the game is 0.49, and to lose the game, 0.30. And that's the end of part 1. I will come back on another video to start part 2. So after you're done with part 1, you can work on the homework and then come to part 2 or watch the next video.